So welcome everyone. We are now in Wednesday of the ninth week. So this is our 18th lecture. Maybe I'll try to put this up next and work backwards rather than forwards because the latest lectures are arguably more important. So let's dive right in with me sharing my screen. And we are on variability. What did we get up to? Anyone remember
We were
specifically?
going to read you the mean absolute value
Ah, yes,
thing.
yes, that's right, because it was a little confusing. Okay. So thank you, thank you, thank you, thank you, thank you. Um, so we were, okay, the mean absolute deviation, that's what we're up to, right? The mean absolute deviation. Okay. So the mean absolute deviation, okay, is another way of considering the data instead of looking at either the IQR or the range. It's our second approach to variability, and I want to start over with that one because last time I had given you one formula and realized somewhat through that the formula wasn't 100% correct, and I thought that might have been confusing. So I want to start over again. So you can kind of ignore that and start from here. Okay, so one way to think about variability in data is to examine how far data values are from the mean. So here we have a group activity. We have 4 Brownie Girl Scout troops. Delara's very excited. They're all Brownie Girl Scouts. She loves that. And each one has 9 girls. And the number of boxes that each one sold is shown. And as we saw last time, the mean for each of them, I believe, was 6. Okay. In fact, part A below says that the mean for each of them is 6. Okay. Um, and the question was which troop, well, I don't really want to do B again because it really doesn't really add to our discussion. What I want to do is as follows. Look at troop A. Okay. So here we have troop A written down. And troop A, what's written is the each value, not only each value, but how far each one is currently from the mean. And when you add up all of the distances from the mean, 4 from the mean, 3 from the mean, 2 from the mean, 1, 0, 1, 2, 3, 4, you get a total distance of 20. Do we agree?
Mm-hmm.
4, 7, 9, 10, 11, 13, 16, 20. The total distance from the mean is 20. Okay. And I had said that that was the mean absolute deviation, but what I neglected to realize or remember was that what you need to do here is not only take this 20, but take this 20 and divide by what number? What number do we divide by?
By 9.
We divide by 9. Why by 9? Because that's how many data points there are. Okay, so what is the mean absolute deviation in this example? It's 20 divided by 9, which is 2.2 bar. Okay, let's do the same thing for troop C. Okay, so I'm going to hold this for a second. I'm going to keep the 20 over 9. Let's look at troop C. And we see for troop C that we have 2 6 6 6 6 6 6 6 6 6 7 6s followed by a 10. So when I go back up to here and I do this again, what we have is 2 6 6 6 6 6 6 6 and a 10. And the question is, what is the mean absolute deviation now? Well, how far is 2 from the mean? Remember the mean was 6. So how far is 2 from 6?
4.
4. And how far are each of the 6s from 6? This is not too tough, or
0.
shouldn't be. Huh?
0.
0. Those are all zeros. And how far is 10 from 6?
4.
4. For a total value when you add them up of how much?
8.
Of 8. Right? You can put in those zeros here if you'd like. And therefore, what is the mean absolute deviation for this one?
8 over 9.
8 over 9. So it's a much smaller value, correct? Yes?
Yes, indeed.
Okay. So the question is the distribution of troop A or troop C more variable according to the method devised by the students? Well, we see that the mean absolute deviation for C is significantly less than the mean absolute deviation for A, right? Which means A is more distributed. It's more variable. It's got a larger variance. It's more all over the place than C. Okay?
Yeah.
All right. So let's now go to, okay.
Professor,
Yes.
is it more scattered because there aren't as many sixes, or just because of the total?
It's more the total. It's more the total. It's not so much how many sixes there are, but it's more the total.
Okay, thank you.
You're welcome. Okay, so let's see what we do here. We have, they just do, oh yeah, so let's do E now. Okay, the students' method worked out well because the troops are all the same size. The students didn't divide by anything, right? The students just calculated the total number. We threw in the division because we remember what happened last time where you have to divide by n. The students didn't do that. That was okay in the students' case because all the sizes, all the samples were the same size. They were all 9. But what if they're not all 9? Okay, if they're not all 9, like this example here. Now there's 40 girls, 20 of whom sold 5 boxes, 20 of whom sold 7 boxes. Okay, what's the average if half of them were 5 and half of them were 7? What's the average if half of them were 5 and half of them were 7? Anyone?
6.
6, right? The average is 6, right? 6 is right in the middle, correct? Yes?
Yeah.
Right? 6 is right in the middle, right? It's the average. Okay. If we calculate what the students did, which is just straight up adding how far each one is from the mean, what we see is that this one is 1 from the mean. This one is 1 from the mean. This one is 1 from the mean. In fact, they're all 1 from the mean. And how many were there altogether?
40.
40. So the students would have gotten a total of 40. Well, we know now that you divide by how many there are. And how many data points were there?
40.
40. And you therefore get a mean absolute deviation of 1. And as you can see, these numbers, even though there's lots of them, these numbers are really, really, really close to 6. So the mean absolute deviation is small. They're not really scattered and far away. Okay, so this leads us to where we left off last time, which is the next page, which is essentially giving us the formula.
I'm a little bit.
Yeah, go ahead. Talara, I can't hear you.
So do we add up all the numbers in the data set and like divide it by how many numbers there are?
You add up how far each one is from the mean, and then divide by how many there are. So in the last example, each one was 1 away from the mean. Right? In the last example, each one was 1 away from the mean, right? And therefore, since there's 40 of them, each one which is 1 away from the mean, the total adds up to 40. And then if we divide by how many we have, which is 40, you get 40 over 40, you get a total mean absolute deviation of 1, right? Which is lovely, a very small number, right? But in general, that's not going to happen. So the mean absolute deviation is the sum of how far each one is from the mean. It's important to remember that they're all 1 away. Sorry, that's not what I meant. That they're all positive, because I don't care if I'm less than or greater than. It's how far away I am. That's all that matters. Okay, it's how far away I am. Each one is 1 away. Whether it's to the left, whether it's to the right, doesn't matter. They're each 1 away. I add up all those positive numbers, and therefore it's a total of 40 divided by 40, and I get 1. Okay, so when I compare A to E, I see that A had a mean absolute deviation of 2.2 bar, and E had a mean absolute deviation of 1. So even though the
So-
total, yeah,
Sorry. That I don't know what that thing is called. That weird looking E.
this is it means add.
Okay, so that, and then the absolute value of x minus x bar.
Yeah, so this just means
That whole thing is sum of how many far away.
yeah, that's all it really means. Add
Okay.
up. It means add up how far each thing away is from the mean. That's exactly what it is. Add up all the distances from the mean. So it's a very abstract way of describing what I said in words, which is just add up how far each one is from the mean. When you add them all up and then you divide by how many there are, that's going to give you the mean absolute deviation. Okay? Okay. You don't know about this. Okay, so that's it for mean absolute deviation. So how many different measures of spread do we have so far? We have the mean absolute deviation. We have the interquartile range, the IQR. And we have the range, although what do we say about the range?
You never use it.
We never use it, right? We never use the range, right? We know it's there, but we never use it. Okay, so we have the range, which we never use. We have the IQR, which we use a lot, and we have the mean absolute deviation. Okay, the next one is called the standard deviation. Now, the standard deviation is basically our third measure of variability after the IQR and mean absolute deviation, and it is without question the most important. So I guess, they saved it for last. Okay. And like the mean absolute deviation, it has to deal with how far every data point is from the mean. So the first thing you got to do is you got to calculate the mean. Unless you're going to have a computer or a calculator do it for you, you have to calculate the mean first. But once you calculate the mean, here's what you do. And it sounds a little complicated, but it's just following the formula. The first thing you do is you calculate the x minus x bar. This part here tells you how far each one is from the mean, exactly like the mean absolute deviation. In the case of the mean absolute deviation, what did we do? We added up we took the absolute value to make sure they're all positive, and we added them all together, correct? Here, we do something different. We square them all and add them all up together. So we're still going to add them, but before we add them, we square them. Now, just like the absolute value, notice that squaring makes them all positive. So whether it's negative or positive, you square it. Now we only have positive numbers. It's just a different approach than the mean absolute deviation, which says, hey, you want it to be positive? No problem. Take the absolute value. Yes, the absolute value will make it positive, 100%, but that's not what we're doing here. We're squaring them all. That's how we're going to make them positive. Okay, and then we add them all together. So and we'll do an example, I promise, but you do every single deviation, you square them all, you add them all together, and then you divide by something. And this is the part that confuses people. What are you dividing by here? What does this formula say? By
the number of data points minus 1.
Yes, you don't divide by the number of data points. That's what you do in the case of the mean absolute deviation. Here, you divide by the number of data points minus 1. And then you do one. Yeah, go ahead.
So just for clarification, sorry, there's a lot of noise behind me. When you add them all together, so if we had that previous problem, troop C,
yeah,
we would add up that 4. We would do 4 squared and then 4 squared and then add that.
For troop C, which was 2, 6, 6, 6, 6, 6, 6, 10, right?
Right.
Yes, so you would do the 4 squared, 0 squared, 0 squared, 0 squared, 0 squared, 0 squared, and so on, 4 squared. That would give you 32.
Right.
Then you would divide by 8 because there's 9 data points, so you divide by 8. That would give you 4. And then you would take the square root, that would give you 2.
Okay, you take this.
At the
Or
very,
whatever
at the
answer
very,
that-
at the very, very end, you take the square root.
Okay, so
Okay, at the very, very end, you take the square root. Okay. And let's do an example to illustrate this. Okay, the standard deviation. Okay, so complete the table on the next page to compute the stand. Oh, I have some text here. Hold on, some messages. I'm so confused. I believe you square each, then add them. Okay, so Talar, what's your question?
So, sorry, it's just very confusing.
Yeah, that's
So
fine.
what's the x in parentheses? Is that like number from our data set?
That's your data point. That's correct. The X in the parentheses, that's your data point. What you do is you take your data point and, well, you know, let's do an example right here. This example, we'll see it in action. Okay, so here we have troop A. Troop A, if you recall, was 2, 3, 4, 5, 6, 7, 8, 9, 10 with a number of boxes sold, right? Very spread out, correct?
Yep.
Remind me, what was the mean again? I forgot.
9.
No, the mean wasn't
No,
9.
6.
The mean was 6. So how far is 2 from 6? What is 2 minus 6?
4.
-4, technically, right?
No, negative.
And what is 3 minus 6?
-3.
-3. And what's 4 minus 6?
-2.
And what's 5 minus 6?
-1.
And 6 minus 6?
0.
And then we have 1 and 2 and 3 and 4. Correct?
Yeah.
Now, notice, by the way, if you add all these numbers, what do you get?
1.
Try it again. If you add all those numbers, what do you get?
0.
You get 0. Which is why it's very important to square them all.
Mhm.
What's -4 squared?
16.
16. Then the negative goes away. What's -3 squared?
9.
Negative goes away. What's -2 squared? 4, 1, 0, 1. Whoops. 4, 9, and 16. Right? You square them all. Do you agree? And then you add them all together. So what do you get when you add them all together?
60.
16, 20, 30, 60. You get a total of 60. What's the next thing to do according to the formula?
Divide by how many data points minus 1?
How many data points were there?
There's 9.
There were 9. So what are we going to divide by?
8.
So we get 60 divided by 8. So I have to erase these because they're getting in the way, but hopefully you wrote them down. Hopefully you wrote them down. So let's go back to here, which is the square root of 60 divided by 8. And for 60 divided by 8, we can just do what? Just take out a calculator, because unfortunately 60 divided by 8 is not going to be a nice number. So what is 60 divided by 8? It's 30 divided by 4, 15 divided by 2, so 7.5. And the square root of 7.5 is about, what, 2.7? What's the square root of 2.5, please?
2.7.
Oh my
3,
God.
8, whatever. But
I knew it wasn't exact, but that's pretty amazing. I gotta say so myself. I see none of you are really applauding or really acknowledging the awesomeness of that, but that's okay. I forgive you. Oh, thank you very much. Thank you. So we get a standard deviation of 2.7. So Talara, as confusing as the formula might have been, does it make sense now how to do it?
A little more, yeah.
Yeah, it's just an
It's
algorithm.
harder when it's actual numbers and not a bunch of letters.
100%. I'm with you loud and clear. That's why we do examples. My personal belief is to do an example, then a generic formula, then another example to kind of reinforce it. But the more you do, the more time it takes. And of course, someone said, "Okay, what happened here?" She's saying,
Professor, I have a question.
that makes sense. Great. Yes, go ahead.
Going back to the table of the deviation from the mean,
Yeah.
how did you like insert the numbers to get the values, the -4, -3, and all that?
Well, 2 minus 6. 3 minus 6, 4 minus 6, right? Each x value minus the mean, and the mean was 6.
Also, that the X with the little line on top, that's indicating the mean.
That's the mean. That's x bar. That is the mean.
Oh, okay, okay, cool.
Okay, that is the mean. Okay, everyone with me so far? Okay, so let's scroll down. What did taking the square root accomplish? So this is more of an abstract thing, and Talara's going to say, I don't care, but that's okay.
I said I don't know.
She likes the concrete. But you'll notice that when you squared everything, you essentially change the units. For example, if I have feet or seconds or pounds or some physical quantity and I square it, then I square the units too. So now I don't have feet or seconds or pounds anymore, but rather I have square feet or square seconds or square pounds or some other abstract quantity squared. So what does the square root do? It brings it back to the correct and appropriate units. Okay, that's the purpose of the square root. Now the better question is, why are we dividing by n minus 1 and not dividing by n? And the truth of the matter is, this is a question that you should know the answer to, or at least be able to say something about, because your students are going to ask it, right? Your students are going to say, hey, why is everything else, or the other one, why is it n, but this is n minus 1, right? Your students are going to ask that. And the answer is, it's really too complicated to say at this level, to be honest. Okay, the reason has to do with the fact that when you use something to estimate something else in statistics, sometimes it comes along with a bias. What do I mean by that? So suppose you take a sample of everyone at CSUN, and you use that sample to approximate the average height of every American. If I say, take the average of that sample to estimate the average height of every American, do you think that would be a pretty good approximation? If I take 40,000 CSUN students and take their average and say, I'm going to use their average as my guess for what the average height of every American is, that's a pretty good approximation, because it's a large sample and it's not like only tall people or short people go to CSUN, right? People of all heights go everywhere. So it's a pretty representative sample. But if I say, you know what? I'm going to take the average height of everyone at CSUN and use the tallest one as my approximation for the average height of every American, do you think that would be a good approximation? Hell no.
It would be biased.
Very biased, right? Very biased. So the reason why we divide by n minus 1 instead of n has to do with the fact that if you divide by n, you have a small bias in your approximator. And if you divide by n minus 1, you don't. That's just what the math gives you. Okay, it's a mathematical determination. N minus 1, no bias. N has a little bias. Now, if n is big, it really doesn't make that much of a difference. But nevertheless, it's there. On your calculator, it usually gives you both. It'll give you the value when you divide by n, and it will also give you the value when you divide by n minus 1. N minus 1 is usually labeled with the letter S, and n is labeled with the Greek letter sigma. So I'm going to write them here so you'll see it, right? The American letter S is for when you use n minus 1. And if you divide by n, then we have the Greek letter sigma, which kind of looks like a sideways 9 a little bit. Okay, so your calculators do both S and sigma. Okay. but you should be using S for a sample. If it's the population, then it's okay to use the other one. But then N is big anyways, and it doesn't matter. So just understand the concept of bias. So let's do another example. It says here Jane has a mean test score of 69 and Jason had a mean of 76. Okay, you can look at, oh, not Jane, Jade. That's a cool name, Jade. I like it, Jade. Anyways, Jade had the mean of 69 and Jason had a mean of 76. Now, if the problem had not given you those means, would I have been able to figure them out anyway?
Yeah.
Sure, because you just add them up and divide by how many you have, right? So the question is, which student had test scores that vary more from their mean? And we're going to do it using the standard deviation. So let's do Jade first. All right, so here's Jade. The first thing we do, huh?
Was there any more of those like chopped up potatoes?
Was there any more of the what?
Chopped up potatoes.
I don't have any, I'm sorry. I already finished them.
Sorry.
So it's my apologies. I mean, I love chopped up potatoes. I really do. But I ran out tonight, so I'm so sorry. But instead, we do have is lots of math. So that's almost the next best thing. Right? So we have lots of math. That's very exciting. So let's do it for Jade. It's going to be the square root. And I already know the bottom. What's the bottom going to be?
68.
The bottom,
5 minus 1.
69 minus 1.
which is 4. There's 5 data points, right? So that's 5 minus 1 is 4, correct? Now, on top, what we have to do is calculate how far each one is from the mean and square it. So the mean was 69. So how far is 20 from 69?
49.
So it's going to be 49 squared. Next, how far is 65 from 69?
4.
4. So that squared is just 16. Notice that I did not square 49. I just don't happen to know it off the top of my head, but I did square 4. How
I'm
far
sorry.
is 80? Huh, sorry.
I'm so confused. Where are you getting those numbers?
How far is 20 from the mean?
But why did we square the
Okay.
other one?
Okay,
Because I knew 4 squared. When I do my calculations, I'll square 49 too. I just don't happen to know it off the top of my head. But before I did know 4 squared, so I just wrote 16. How far is 80 from 69?
29.
80 from 69?
it's 11. So 11 squared is 121.
121. How far is 85 from 69?
16.
16 squared is 256. And how far is 95 from 69?
26.
26. And I don't know 26 squared. So I'm going to do the same thing I did for the first one and just write 26 squared. And I have no idea what that is. But at the end of the day, we're taking out a calculator anyway. So when I take out my calculator and I do 49 squared plus 16 plus 121 plus 256 plus 26 squared, and then I divide that by 4, and then I take the square roots, I get approximately 29.5. So my standard deviation is 29.5. Okay. Now we can do Jason.
$29.5.
That's what I got. Did you guys not get the same thing? Did you guys not get that?
I got that.
Okay. Good. So let's do Jason. I'm going to give you guys a couple seconds to get ahead of me. Go ahead. Okay, so I'm going to start filling in numbers here. What was Jason's mean again? It said it, but I'm covering it up, so I forgot it.
I think 76.
76. Okay. So which one had the higher standard deviation?
Jade.
Jade by far, correct? Where did the 4 come from? Which 4? Well, there's 5 data points, so subtract 1, n minus 1.
Okay, thank
Alright.
you.
All right, 5 data points, so n minus 1 is 4, then you square roots, and then you take out a calculator, because these are not nice numbers. So without nice numbers, right, you take out a calculator. Agreed? Make sense?
Yes, thank you.
Okay. Okay, so let's take a look at this one. It says here, each distribution below has roughly the same mean and range. Remember, the range is largest minus smallest. What is the mean for each of these approximately? Take a look at these 3 pictures. And the claim is that all of them have roughly the same mean. So what is that mean?
Is it 5?
Now 5 is over here. That's not, doesn't look like the average or the balance point.
Like 3.5.
Mm, 3.5. Yeah, 3.5 looks good. What do you guys think about 3.5?
Sure.
Maybe 3.6 because the right sides are all just a little bit taller than the left sides, aren't they?
If we put 3.5 on a quiz or a test,
Oh, I wouldn't take off points for that. No, I wouldn't take off points for that. But 3.6 looks a little bit closer. Would you agree? Yes, a little bit
Yeah.
closer. So 3 points. Of course, if I had actual data, I would compute it. But the mean looks to be about 3.6. And what does the range for all of them look to be about? Or exactly? What's the range exactly?
5.
5. 6 minus 1, 5. Now, which of these has the largest standard deviation? And which one has the smallest? So remember what standard deviation is measuring. Like the mean absolute deviation, the standard deviation is measuring essentially how far the data points are from the mean. Whichever one has data that is in general close to the mean is going to have a small standard deviation. Whichever one has data that's far from the mean is going to have in general a larger standard deviation. So which one of these 3, A, B, or C, has data which is closest to the mean?
Say B.
B, right? In B, it's high near the mean and it tapers off on the sides. So that while there are some that are far away, there's a lot that are close. So that's going to have the smallest standard deviation. And which one's going to have the largest standard deviation?
What was the smallest again?
The smallest is, well, you tell me. Forget about repeating it. You tell me which is the smallest. Walk me through it. Which one's the smallest? If you're just writing down the answers, you're not getting what you're supposed to be getting, which is understanding of why. So talk to me. Which one do you think is the smallest?
Professor, I stepped out of the room for a second. Can you go over what you said about it? Like I walked back when you said something about
The standard deviation measures how far the data points are from the mean. Okay, whichever one has lots of data near the mean is going to have a small standard deviation or a smaller standard deviation. Whichever one has lots of data points far from the mean is going to have a larger standard deviation. So which one of these three has the majority of their data points near the mean?
Would it be B?
It would be B, because in B, you see that it peaks near the mean and it tapers off on the sides. Which one has the largest standard deviation according to that?
A.
A, right? A has the majority of them far away and a few of them that are close. And how about C? C is basically somewhere in between. Does that make sense?
Yeah.
So let's compare the three measures of variability, okay? Because different situations call for different ones, okay? So you have learned three ways to measure the variability of a distribution. Well, four technically, but remember we don't talk about that one. You have the IQR, that's the interquartile range. You have the MAD, the mean absolute deviation, and then you have the standard deviation, correct? So often, but not always, when comparing distributions, each of them will give the same answer as to which has the most variability and which has the least variability, okay? But not always, okay? So in general, the IQR is the most useful when the distribution is strongly skewed or has outliers, okay? So when you have a strongly skewed distribution or one with outliers, the IQR is the appropriate one, okay? The standard deviation is the most commonly used one. It has the best mathematical properties, and it's most useful for symmetric distributions, okay? The MAD is used mainly to introduce the idea of deviation and is never actually used in practice, which is kind of why I didn't really have it fully internalized, because I never use it because it's just not used, okay? Now, let's go a little deeper here. If the mean absolute deviation is 0, if you get a 0 value for the mean absolute deviation, what does that tell you?
That your mean is 0?
No, not necessarily. The mean can be anything. Remember, the mean absolute deviation tells you how far, well, I mean, how do you calculate it? You look at how far each one is from the mean, you add them all up, and you divide by n, correct? So if that number is 0, then what can you conclude?
There's no data points.
No, there could be lots of data points.
All the data points are on 0?
Not on 0.
What?
What? It tells you that all the data points are equal to the mean. If all the data points are equal, they're all the same number, whatever number that is, it could be 1,000,000.
Oh, okay.
All the data points are the same number, then each one is 0 from the mean, so that when you add them all up, you're going to get 0. So if the MAD is 0, it tells you that they're all the same number. What about if the standard deviation is 0? What does that tell you? What does it tell you if the standard deviation is 0?
Would it be that all the data points are 1 away from the mean?
Nope. Look at the formula and tell me what has to be true if the standard deviation is actually equal to 0.
Would the mean have to be 0?
No, the mean could be anything.
Okay.
But I mean, I love guessing. Even if it's wrong, I have no problem with that. I love thoughtful responses. So like the MAD, it tells you that all the data
But
points
it-
are. Oh crap! I was already starting. Go ahead.
I mean, I'm probably wrong, so you keep going.
Who said that? Why would you think that?
Oh, well. Anywho,
Yeah.
if like when you add them all up and divide by 0, if that equals 0,
Well, you're not dividing by 0. You're dividing by the number of data
or
points.
I mean, yeah, but if the top is 0,
Yeah. So how can you have a topping 0 if you're adding a bunch of stuff?
Would
That
it
your
be
data points are on 0?
Sorry?
Is it that your data points are 0?
Data points could be anything.
like the first one? It has to be equal to the mean.
That's correct. All it tells you that all the data points have to be the same. They can be any number, but they all have to be the same so that the distance from the mean is 0 for all of them. Okay, it doesn't tell you about what they're equal to. They can be equal to anything as long as they're all the same number. That's the key. They all have to be the same number. Okay, now, what if the IQR is 0? What does that tell you?
The same thing.
No. But
But
good
if-
guess. Good guess, but no.
But you're subtracting with Q3 and Q1 for the IQR. So they
Yeah.
have to be the same number for that to turn out to be.
You're right. That tells you that Q3 minus Q1 must be 0, correct?
Yeah.
Which means Q1 and Q3 are the same. But remember what Q1 and Q3 are measuring. Q1 says 25% or less than this number. And Q3 says 75% or less than this number, correct? So what it's telling you is that the middle 50% must all be the same.
Oh, wow.
But the outside 25, 50%, 25 and 25, those could be anything. Which is why the IQR is useful when it's skewed, because the middle 50% is all that matters for the IQR. So it kind of, in some sense, reduces the skewness. Does that make sense?
Yeah.
I hope it does. I hope it does. And that concludes chapter 13. And we're not going to start a new chapter with only a few minutes to go. So we will end here. I'm going to stop sharing and I'm going to stop recording.